So by now, you're no stranger to the James Webb Telescope. Although you've been given heaps of cool information about it this evening, what hasn't been spoken about it yet is the observation targets and scientific goals it aims to achieve. If you're just joining in now, let me give you a little recap on the James Webb Space Telescope. The James Webb Space Telescope, which was launched at the Earth's atmosphere on the 25th of December 2021, is the world's largest, most powerful, and most complex space science telescope ever built. The objectives Webb wishes to solve include the mysteries in our solar system, to look beyond the distant worlds around other stars and probe the mysterious structures and origins of our universe and our place within it. Unlike other telescopes that travel throughout the Earth's orbit, the James Webb Telescope's primary aim is to shed light onto our cosmic origins, exploring the first ever galaxies that burst into life, revealing the birth of stars and planets that formed out the darkness of the early universe, and look for exoplanets that could sustain potential life. The observation targets that the JWST has to behold are broken down into 4 categories: the early universe, star life cycles, galaxies over time, and other worlds. So let us begin in breaking those goals one by one. The further we look back in space, the earlier we look back in time. Right now, the best bit of equipment that allows us to look back at the beginning is the Hubble. However, in 2021, the Hubble took a back seat in the popularity bus and came along the James Webb. As you know by now, the JWST uses a little thing called infrared vision. Its infrared vision allows Webb to study stars and planetary systems that have formed inside the thick cosmic clouds of gas and dust that are opaque to visible light. If you were to compare its strength of infrared vision to other telescopes, such as the Hubble, the James Webb is a lot more powerful. The Hubble Space Telescope can only pick up to 90 to 2,500 nanometers of light, whereas the James Webb Telescope can detect 600 to 28,500 nanometers of light. With this extra boost of advanced technology, Webb hopes to address several key questions that can help us unravel a story of time. A couple examples include: when and how did reionization occur? What sources caused reionization? And what were the first galaxies? To find the first galaxies, Webb will make ultra-deep near-infrared surveys of the universe and follow up with low-resolution spectroscopy and mid-infrared photometry, which is the measurement of the intensity of an astronomical object's electromagnetic radiation. To study reionization, the James Webb high-resolution near-infrared spectroscopy will be needed. Galaxies are an important topic in space observation because they show us how the matter in the universe is organized on large scales. Said this, galaxies are the primary focus of the second observation target, specifically how galaxies formed over time. Some of the questions Webb wishes to answer include: how are galaxies formed? What gives them their shape? How are the chemical elements distributed through the galaxies? How do the central black holes in galaxies influence their host galaxies? And finally, what happens when small and large galaxies collide or join together? The James Webb Space Telescope will observe galaxies far back in time and hopefully answer these questions. By studying some of the earliest galaxies and comparing them to today's galaxies, we may be able to understand their growth and evolution. Webb will also allow scientists to gather data on the types of stars that existed in these early galaxies. Follow-up observation using spectroscopy of hundreds and thousands of galaxies will help researchers understand how elements heavier than hydrogen were formed and built up as a galaxy formation proceeded through the ages. These studies will also reveal details about merging galaxies and shed light onto the process of galaxy formation itself. Today we know that stars are the essential sources of raw material in the universe. From recycling and distributing the elemental building blocks of everything we observe, new stars such as nebulas of gas and dust, planets, and even humans. All life on Earth contains the element carbon, and all the carbon was originally formed in the core of a star. Stars populate the universe with elements through, like us, a life cycle. From new stars, nebulas of gas and dust, planets and even humans to the end of their life, when they become supernovas and black holes. To unravel the birth and early evolution of stars and planets, we need to be able to peer into the hearts of dense and dusty cloud cores, where star formation begins. These regions cannot be observed at visible light wavelengths, as the dust would make such regions opaque and must be observed at infrared wavelengths. That's where the Webb comes in. The continual discovery of new and unusual planetary systems has made scientists rethink their ideas and theories about how planets are formed. Scientists realize that to get a better understanding of how planets form, they need to have more observations of planets around young stars, and more observations of leftover debris around stars, which can come together and form planets. Using Webb's infrared technology, we aim to uncover some of these universal mysteries. One of the main uses of the James Webb Space Telescope will be to study the atmospheres of exoplanets, to search for the building blocks of life elsewhere in the universe. The first planet outside our solar system was discovered in 1992. Since then, we've discovered many planets around other stars, making scientists conclude that planets are actually quite common. The ultimate objective of the search is to find planets orbiting in the habitable zone of the star, or also known as the Goldilocks zone, where it is possible for liquid water and perhaps even life to exist. But Webb is an infrared telescope, you say. How is this good for studying exoplanets? One of the techniques Webb will be using for studying exoplanets is the transit method, which means it will be looking for the dimming of the light from a star as a planet passes between us and a star. Astronomers call this a transit. Webb will also carry coronagraphs to enable direct imaging of exoplanets near bright stars. The image of an exoplanet would just be a spot, not a grand panorama, but by studying that spot, we can learn a great deal about it. That includes its colour, differences between winter and summer, vegetation, rotation, and even its weather. In addition to studying planets outside our solar system, scientists want to learn more about our home. Webb complements NASA's other solar system missions, including those on the ground, orbiting Earth, and in deep space. Data of different wavelengths and from diverse sources can help scientists build a broader, fuller picture of objects in our solar system, especially with the help of Webb's unprecedented improvements in sensitivity and resolution. Webb will observe Mars and the giant planets, minor planets like Pluto and Aries, and even smaller bodies in our system, comets, asteroids, and other objects. The James Webb Space Telescope, whilst only young in age, has revealed so much in its mere 2 years of space exploration. With its high-definition technology and remarkable infrared system, the James Webb will unravel so much in the many years to come, and hopefully not only answer some of the questions that I've mentioned this evening, but also what happened at the beginning of it all, the beginning of the universe itself. My name is Ella, and I hope you have a wonderful rest of the evening.